All right, wonderful. Next up this morning, we have Madeline Overton, who's joined us from San Diego State, where she'll be a rising senior. She's been working this summer with Andrew Benson, and today she'll tell us about her project, improving the accuracy of the subhalo mass function by characterizing halo finder completeness. Go ahead whenever you're ready.
Hi, thank you, Glenn, for the introduction, and welcome everybody. I'm excited to share all that I've learned this summer and what I've been working on. So first, I'd like to show this video of the evolution of a dark matter halo, and this shows how a small overdensity in the early universe snowballs into clumps of dark matter, which we call halos, and embedded within them, smaller clumps, which we call subhalos. As a halo forms, it pulls normal matter along with it so that galaxies and other interesting objects can form at the center. This is also an example of an n-body simulation, which we use to test how different models of dark matter behave, and specifically how different models make different predictions for the amount of substructure in the universe. Then, once you have your simulation, a tool called a halo finder is often applied to identify halos and subhalos from the output of the simulation. This is an important piece of the puzzle because it can essentially give a measurement of how much substructure is predicted by a given model of dark matter. Halo finders are also critical for comparing simulations to observations. One such observation that we can indirectly detect dark matter with is strong lensing. And so the way that this works is represented by these images below. So first, we need to find an image that is being lensed by a dark matter halo. Then we construct a model of what kind of lensing image would be created by a dark matter halo with no subhalos. And then when you subtract off the model from your actual data, it reveals lensing due to just the subhalos. And this is exciting work because it allows the simulations of dark matter and the substructure to be compared to what's actually out there. And so halo finding algorithms are involved in so many big science questions, so many science questions that are surrounding the subhalo mass function. And so the two examples I've just gone over are being able to analyze dark matter model predictions for substructure. And this is a big determining factor for finding the best candidate for a dark matter model and constraining the dark matter particle. They're also necessary for making comparisons between simulations and observations. And so this also will allow us to improve on simulations and our models as well. And so since halo finders are involved in so many different kinds of projects, it's a concern that halo finders might be missing some subhalos because that would affect the analysis and any kind of work that is using these halo finders. And so that comes to the purpose of my project. So I'm working with the halo finder called Rockstar in order to find its detection efficiency. And then our measurement for the detection efficiency can be used to correct the count of subhalos given by Rockstar and correct the number of subhalos found by Rockstar to get the true number of subhalos that your model is predicting or your simulation is giving you. And so our main questions in this project have been, when does Rockstar find a subhalo? And then how well is Rockstar able to find the subhalo? And then also, what properties are most influential on Rockstar's ability to detect the subhalo? And so I've been using the halo and subhalo generating capabilities of Galacticus, a program developed by Andrew Benson. And so I've been creating controlled realizations of subhalos with known properties. And the output of Galacticus is a very idealized n-body simulation. So I've been creating very smooth and spherically symmetric subhalos. And so my work has been focused on creating many different realizations of various subhalos, each with a random set of particles and then testing how well Rockstar is able to recover the mass of the subhalo at different masses and different positions for the subhalo. And so I've been testing subhalos within a range of 2 times 10 to the 8th to 3 times 10 to the 11th solar masses, and within a range of 5 to 200 kiloparsecs from the center of the host halo. And so far, this is how the overall detection efficiency is looking. And so the overall detection efficiency is primarily affected by very low mass subhalos. And under about 2 times 10 to the 8th solar masses, the detection efficiency drops off substantially. Under 2 times 10 to the 8th solar masses, subhalos are also realized with fewer and fewer particles, which also makes the counts by Rockstar very uncertain within that mass range. At the beginning of this project, we were mainly concerned with Rockstar missing subhalos, but there also is some cases when Rockstar actually finds extra subhalos that I did not put there with Galacticus. And so this is represented by those points over 100% detection. And so we are also concerned about these extra subhalos and would like to include that in the correction. For the subhalos that are found, there's a general trend where for smaller and more centrally located subhalos, Rockstar returns the mass less accurately. However, for the most small and most centrally located, there's actually a boost in the detection efficiency or in the accuracy of the detections. And so there's a couple properties of Rockstar that we think might be causing this extra boost. And one of those is Rockstar's minimum particle parameter. And so there's actually a minimum number of particles that Rockstar will even consider calling a halo. And so as we approach that limit, it internally rejects any underestimations for the mass. And so even though less subhalos are being found, of those subhalos, the mass is more accurately returned. As for very centrally located subhalos, we believe that more host particles are being misidentified as belonging to the subhalo. And so this also artificially boosts up the mass of those very small, very centrally located subhalos. And so I wanted to make sure that I wasn't confusing any effects from mass and distance. And so even when they are are plotted together, we still see the small clump of internally corrected subhalos that are a little more accurately returned than those around them. We also still see the general trend that for larger, more distant subhalos, Rockstar starts to recover them more accurately. But as you continue to even larger, even farther subhalos, the masses are actually overestimated. And so these are the kinds of parameters that we're tracking and looking at to see how well Rockstar is doing. And so I'm excited to keep working on this project. And some of the things that I'd like to do are also investigate the effect of the mass fraction loss to tidal forces and how that is affecting Rockstar's detection efficiency. It's also necessary to increase the statistical precision by realizing more subhalos, and particularly in the low mass range where the effects are bigger. And finally, we intend to fit a function to our results so that they can be applied to simulations. And so I look forward to sharing those findings with you as well in the future. But for now, thank you very much for listening.
Nice job, Madeline. Johanna, do you have a question?
Yes, I was just wondering if you have any hypothesis for what's happened, like why you're getting like mysterious rogue galaxies that you didn't put in there.
Yeah, so for very large subhalos, a lot more particles are being realized. And so especially in very dense regions, that one large subhalo could be maybe being split into two smaller ones. And so it's kind of tricking Rockstar into thinking there might be two there instead of just one big one.
And is there like a quick fix for that? Like that you think would address that, or might take some more work?
I'm not completely aware of all the internal workings of Rockstar. So I do not know if there's exactly a quick fix.
Okay.
I guess
it seems like it's not a huge concern. Like it's doing very well. So
exactly,
okay.
Rockstar, yeah, it's widely used, so it is doing its job very well. We just want to be able to tune up some of the situations that it might be making mistakes.
Okay, thanks.
Excellent. I think we have time for one more question. Alex, did you want to ask one?
Yeah, thanks, Madeline. This is really neat. I've spent a lot of time with Rockstar, so it's really cool to see. I was wondering about the sort of the velocity. So you talked about setting them at different distances and different masses, but I was wondering about the velocity that you put the subhalos at, because Rockstar also uses like how fast the particles are going as part of the halo finding, I think.
Right. We said that that's at we've not been varying the velocity. So that's also another parameter that we could look into. I want to say that it's around, I'd actually have to check back and see what exactly that is because we haven't been working with it. But yeah, that is definitely something that we could look into.
Awesome. Thank you so much.